Hi, everyone. Welcome back to Dave's Math Channel. I'm your host, David Tare, and today I'm going to talk about a very important number in mathematics, the number given the symbol E, also known as Euler's constant, or sometimes known as the base of natural logarithms. Anyway, I think after pi is probably the next most important mathematical constant most people consider that it is. And so what exactly is E? Well, like I said, it's called Euler's constant or Euler's number. This is kind of a brief description of what it is. It doesn't really define it, but it says there's a number called E. It's also known as the base of natural logarithms, and it's used all over math. But it's basically it's used in exponential functions mainly. I mean, I'll get to that later, but anyway, what exactly is E? Um, well, here's the first 2,000 digits of E. It's an irrational number. Goes on forever, like pi. It starts out 2.71828, and it's known to probably millions, maybe even billions of digits, like pi. I don't think it's known as many digits as pi, but it is known to some insane number of digits. In a previous video, I think in the last video I made, I defined E this way. I mean, either the thing about E, I guess the reason why E isn't as well known as pi has a very, very simple definition. Pi is just the ratio of the circumference to the diameter of any circle. Very easy. I mean, any grade schooler can understand that. But for E is a lot more complicated. I mean, E wasn't even discovered until the 18th century. It was named after a very famous mathematician named Euler, who I think first discovered it. I'm not 100% sure about that. It might have been Jacob Bernoulli. I know that I don't think he called it E, but he may have actually discovered E before Euler, maybe in the late 17th century. But I think the reason why E isn't as well known is because it mostly is used in calculus. Most students don't learn about E until they learn calculus. It has a much more complicated definition. It's not as easy to define as pi. But it is very, very important, and I'm going to try to emphasize how important it is in this video. So here's one definition: is a limit, and limits are probably the most basic concept in calculus. You don't have to know much. You don't even really have to know any calculus to understand this definition. I explained it in my previous video where I talked about compound interest. If you just imagine you put money in a bank account that pays uh, compound interest. N is the number of times it's compounded every year. If you started with $1 and compounded N times a year, and you kept it in the bank for N years, you would have a certain number of dollars after 1 year. And that number of dollars approaches E as N goes to infinity, which means if you had it continuously compounded, you would have E dollars after 1 year. I think that's the easiest way to explain what E is. But anyway, there's a lot more formulas for E. This is actually a better formula, I think, because it converges a lot faster. You don't need very many terms. These numbers in the denominator of this formula, these are called factorials. So 0 factorial is defined to be 1. After that, n factorial is just the product of all the integers up to positive integers up to n. So 1 factorial is 1, 2 factorial is 1 times 2, 3 factorial is 1 times 2 times 3, so on. They grow very, very fast. That's why this series converges very fast. And it converges to E, and you don't need very many terms. I mean, with just 10 terms, I believe you can get E to 6 decimal places. So this is a very rapidly converging series, and it's a nice formula for E. And here's a really remarkable formula. This is called a continued fraction. I don't know how many of you guys are familiar with these things, but uh, here's how you can think of it. If you just take the first term is 2. So that's the first estimate of E. It's not a very good one. E is actually closer to 3 than 2. It's about 2.7, but then you just take 2 plus 1 over 1. That gives you 3. 3 is closer to E than 2, like I just said. You take the next fraction, 1 over 2. And that gives you, I think, 8/3, and you keep going like that. You get better and better rational approximations of E. This is a pretty remarkable formula because what it shows is that the continued fraction of E actually has a pattern. And this isn't true of pi, by the way. Nobody's found a pattern in the continued fraction of pi, although this is very nice continued fraction of E. 212, 114, keeps going like that. 116, 118, 1110. Who would have thought, right? But it's a nice formula for E. And here, I probably should have made this thing bigger, but maybe I can right here. Yeah. So here's a definition. Here's another definition of E. This is in terms of the area under a hyperbola. The graph shown is the graph of y equals 1 over x. That's a curve called a hyperbola. And if you take the area of the region of the hyperbola from x equals 1 to x equals e, shown here, this area is equal to 1. Pretty remarkable. And actually, you don't have to just go to e. You can go to any number you want, call it x, and then it'll turn out that the area is equal to the natural logarithm of x, which is kind of the inverse of the exponential function. So it's a logarithm, which is pretty remarkable. So anyway, yeah, e comes up in this formula as well. Let me make this smaller again so I can redo my slides. But yeah, I have to fix this now. Sorry about this. Yeah. Anyway, yeah, I might have to redo this video. Anyway, yeah, that's the area in terms of natural logarithms, and the next slide I have, yeah. So this is just a continuation of the last slide. Where does e come from? Well, it's a type of logarithm. The natural logarithm is ln x is equal to the base e logarithm of x, where e is 2.71828 approximately. That's kind of what the last graph was showing, and like I said, the inverse of a logarithmic function is the exponential function. And actually, there's you can have an arbitrary base. This number e in this formula, y equals e to x, is called the base of this exponential function. You can have any base you want. You can have base 2. That's a little more intuitive. Just a function. Y of 2 to x, that means y of 0 is 1, y of 1 is 2, y of 2 is 4, so on. This is base e, which means y of 0 is still 1, y of 1 is e now, y of 2 is e squared. It grows faster than 2 to the x, but not as fast as 10 to the x, because 10 is bigger than e. But what's remarkable about this particular exponential function is it's the only one where the slope, you can imagine drawing a tangent line at x equals 0 and y equals 1, that line has a slope of 1. And this is the only exponential function for which that's true. So that makes this exponential function kind of special compared to all others. E is a very, very useful function. I mean, e to the x. And actually, one of the most useful properties of the exponential function e to the x, it's equal to its own derivative. This is a very important fact in calculus. That's why this makes this function e to the x so special. It's the only function, let me go back to the last slide. It's the only function for which at each point the slope, that's called the derivative in calculus, but you don't have to know what that means. Just imagine drawing a tangent line at any point on this graph. Then you can measure the slope of that tangent line at any point on this graph, and it turns out the slope for every point you pick is equal to the value of the function. And that's the only function for up to a multiplicative constant. That's the only function in the world for which that's true. And that's a very, very special property of the function e to the x. Other exponential functions are almost as good, not quite. They give you a derivative that's not quite equal to the function you started with, but it only differs by a multiplicative constant. For instance, if the base is a, where a is an arbitrary positive real number, then the derivative of a to the x turns out to be a to the x times the natural logarithm of a, which is just a constant. So that's a very useful property of exponential functions. But as you can see, it's especially nice for e to the x if you choose the base e. That's why e is an important number. And e has, e, this is probably the most amazing. A lot of people think this formula, e to the I pi plus 1 equals 0. This is known as Euler's identity. And a lot of people think that this is the most amazing formula or the most amazing equation or identity, whatever you want to call it. It's the most amazing mathematical equation. A lot of mathematicians think this. It really is amazing. I mean, look at this. This formula on top, e to the I pi plus 1 equals 0. This formula has probably the five most important mathematical constants: 0, 1, uh, E, which I just talked about, I, which is the imaginary unit, and pi, which everybody knows, all in one equation. And who would have thought? I think this is an amazing formula. It's almost like the unified field. I think of it as the unified field theory of math because it's so beautiful. But Euler discovered this equation. It's actually a special case. I'm going to enlarge this again. It's a special case of this other formula in this picture, e to the I phi. I don't know if you can see this, but right below it, this is a unit circle in the complex plane. I talked about complex numbers in a previous uh, lesson on this channel. And I even talked about this formula. And this is where this comes from. E to the I phi. That's a weird thing because you're taking e raised to imaginary power, pure imaginary power. You might even wonder what the hell that means, but it turns out that it's equal to cosine of phi, which is just a trigonometric function of the angle phi, shown here in this circle diagram, plus I, the imaginary unit, times the sine of phi. Amazing formula. When I first saw this formula, I was just so awed by it. I mean, I was at loss for words. I remember I was in a library at the University of Michigan where I was going to college at the time. I picked up a book on I think it was like mathematics for engineers, and I stumbled across this formula, and I just couldn't believe it. I mean, I saw a similar formula to this when I was in high school. It's called de Moivre's formula, but it doesn't involve this e to the I phi. It just says cosine phi plus I sine phi is a nice representation of complex numbers, and it has a lot of nice properties. Um, and then I stumbled across this. I was at a loss for words. One of the most amazing moments of my life when I first saw this formula. Um, but anyway, enough of that. What else? So yeah, the last thing I'm going to say is, there's many applications involving E. This is another one. This is the bell curve, um, discovered by Gauss, I think around 1810. I think most of you guys are familiar with this. It's used all the time in the statistics. It has several different names. Bell curve is the most common one, but it's also called the normal distribution or the Gaussian distribution. And it's one of the most important distributions in statistics. And look at the formula for it. You can actually compute a formula for this bell curve, and that formula turns out to involve, of all things, e again. It also involves pi, square root of 2 pi, which is kind of weird. I think I talked about that in my video on pi, but it involves pi and it also involves e. Look at the exponential term, e to the minus x minus u quantity squared over 2 sigma squared. Don't get too scared by that. All it really means is in the standard form, it's just e to the minus x squared over 2. Mu is the mean of this distribution. Sigma is the standard deviation. The standard normal distribution has a mean of 0 and a standard deviation of 1. So for that case, it's just e to the minus x squared over 2. So now you got, it's not an exponential function anymore because it has x squared in it instead of x. But pretty amazing that the formula for the bell curve, which is one of the most important concepts in statistics, also involves e and pi. So they're obviously both very important numbers. And that completes my lecture on E. I hope you enjoyed it, and I'll see you next time.